Hello friends, welcome back to my YouTube channel. In this video, I will be continuing my discussion on distillation. This is part 18 of my discussion on distillation, and today I'll be talking about energy balance for a typical tray column. In my earlier videos on distillation, to be precise, in part 16 and 17, I have been talking about rectification, that is distillation carried out in tray columns. So in my earlier videos, I have discussed material balance for a typical tray column, and today in this particular video, I'll be talking about energy balance for a typical tray column. So let us begin the discussion. So first, I'll show you a typical tray column. So you have a number of trays in a typical tray column. So these dash lines, they are representing trays. I have numbered those trays from the top. So first is at the topmost tray. I'm calling it as first plate, whereas the last tray in the column, which is at the bottom, I'm calling it as nth tray. Then feed is entering on one of the tray that is located near about at the center of the column. The plate on which feed enters, that is the feed plate. Okay. Then remaining trays I am numbering in this way. So this is nth plate, this is mth plate, and this is m plus 1 plate. Okay. So now as the feed enters, it flows down to the bottom. From the bottom it is removed, and then it is sent to a reboiler where QR is the rate of heat input. The purpose of providing heat is to boil the liquid solution so as to create the vapor phase. Once the vapor phase is created, the resulting vapor phase is admitted at the bottom into the column, and the vapor phase then rises through the column. It is taken out at the top and then sent to a condenser where heat is removed from those vapors at a rate of QC, and the resulting condensate, then it is divided into two parts. One goes back to the column, whereas the other one is taken out as the product. We call that as distillate or the top product, and it will be identified by this parameters. Very shortly I'll tell you what are these parameters. Okay, so other part of the condensate that is coming out of the condenser is sent back to the column. Of course it is a liquid stream, and we call that liquid stream as reflux. It is identified by these two parameters, L0 and XD. So after entering the column, the reflux stream or the liquid flows down, and operation continues in this way. Feed is continuously entering, it is continuously taken to the reboiler, vapor phase is continuously created, the vapor phase continuously flow upward into the column, then taken out at the top, sent to the condenser, then you have reflux stream and then the distillate stream. Okay, so now let us move ahead. Okay, at the bottom there is one more product stream that is taken out from the reboiler, the residue stream is taken out, bottom product. The other name for residue is bottom product, and it will be having this properties W, XW, HW. I will shortly tell you what are this. Okay. Then you also know section of the column above the feed plate. This section we call that as rectifying section. Why it is called rectifying section, I have discussed in one of my previous video. You please go and watch that video. You please do watch that video. Then the section below the feed plate is the stripping section. Again, why it is called stripping section, I have discussed it in that video. You please watch that video. Okay. So this is the typical tray column. Now let us know about the feed solution. The feed solution in this case is a binary liquid solution. There are two components, component A and B. Out of A and B, A is the more volatile component. F is the molar flow rate, moles per unit time. It may be kilomoles per second, kilomole per hour, so on and so forth. F is the molar flow rate. XF is mole fraction of A, which is the more volatile component in feed solution. So XF is mole fraction of more volatile component in the feed solution. In this case, the more volatile component is E. Then HF is enthalpy per unit mole, enthalpy per mole. It could be kilojoules per kilomole, for example. So HF represents enthalpy per unit mole of the feed solution. Okay, then the distillate stream. Let us talk about the distillate stream. D is the molar flow rate for the distillate stream. XD is mole fraction of more volatile component in the distillate, that is mole fraction of A in it. HD is enthalpy per unit mole of the distillate. Okay. Then for the bottom product or the residue, W is the molar flow rate, XW is mole fraction of A in it, that is mole fraction of more volatile component in it. HW is enthalpy per unit mole for the residue or the bottom product. Then the reflux stream, molar flow rate is L0. XD is mole fraction of A in it, and you might have noticed that mole fraction of A in reflux is same as that in distillate, and you can easily understand once the condensate is coming out of the condenser, it is simply divided into two parts. There is no any composition change. It is just divided into two fractions. That's why in reflux also mole fraction of A will be XD, same as that in the distillate. Same is the case with enthalpy. Enthalpy of that stream will also be same as that of distillate. So HD again will be enthalpy per unit mole for the reflux stream as well. I hope this is clear to you. If you have any doubts, you please mention your doubts in the comment section. Then let us talk about the reboiler. So what is happening in reboiler? Heat is added. What is the purpose of doing that? The purpose is to create vapor phase out of the liquid solution. So I'm using a notation of QR, and it represents the rate at which heat is added in the reboiler. And similarly for condenser, heat is removed from the vapor, and the rate of heat removal I'm denoting it by QC. Okay, so I hope you have understood what terms I am using in my discussion. Okay, now let us move ahead. Now let us go for the energy balance for the rectifying section. So we will understand energy balance part by part. To begin with, we will first understand energy balance for the rectifying section of the column above the feed plate. Let us understand. So again, I am showing you the column. So we are going to talk about the rectifying section, this section, that is section of the column that is above the feed plate. So now I have encircled, uh, I have drawn an envelope around the rectifying section, and now you can see the rectifying section. So you should know what streams are. So this is the stream that is going out of the rectifying section. This is the stream that is entering the rectifying section, and of course we have numbered the plate. I have discussed about it. So this is end plate and this is the first plate. There will be some more plates between first and nth plate. The point to note is this stream enters the rectifying section, this stream comes out of the rectifying section, this stream comes out of the envelope that we have drawn, and as heat is coming, it is taken out of the envelope. Okay, now let us understand. Let us first write the energy balance for the condenser. So for that I am again showing you the section, and for our discussion let us use this notation. This stream that is leaving first plate, liquid stream that leaves first plate, will be identified by this notations. L1 represents its molar flow rate, X1 represents mole fraction of A in it, and HL1 represents enthalpy of that liquid. Enthalpy of the liquid that is leaving tray number 1. Similarly, this is the liquid stream that leaves nth plate. Accordingly, it will be identified as Ln, Xn and HLn. Ln being the molar flow rate, Xn the mole fraction of A in it, HLn is enthalpy per unit mole for the liquid stream that leaves tray number nth tray. Okay, now the stream, the vapor stream that is entering, and then it will be going to nth plate. So this stream is coming from a plate that is next to nth plate. Plate next to nth plate will be n plus 1th plate. So that's why the vapor flow rate will be identified as Gn plus 1. Yn plus 1 represents mole fraction of A in it, and Hgn plus 1 represents enthalpy of vapor per unit mole. Enthalpy of the vapor that is coming from n plus 1 plate. So you must have noticed each of the stream, or we are identifying the stream uh, with the with subscript that denotes the tray from which it is coming. So for example, this is Ln, liquid stream coming from nth plate. This is Gn plus 1, vapor stream coming from n plus 1th tray. Now you can easily write notations for this. This is vapor stream coming out from nth plate, so it will be identified as Gn, molar flow rate, Yn, mole fraction of A in that stream, Hgn, mole fraction, enthalpy per unit mole of the vapor stream. So this will be G1, Y1, Hg1. Now this stream, the vapor stream that is coming out of tray number 1, it will be taken out of the column. So it will again be G1, Y1, Hg1. It will be sent to the condenser where it will be condensed by removing heat at a rate of QC. Okay, so now here in order to understand the concept in a better way, I have shown condenser separately. So this is the condenser stream coming out of the column with this notation G1, Y1, Hg1. It is going to the condenser. QC heat is removed. Heat is removed at rate QC, and then you have two streams, the reflux stream and the distillate stream. So distillate is identified by this parameter, so D, XT, HT, and the reflux stream will be identified by L0, XT, HT. You please note, flow rate of distillate and reflux, they are different, but mole fraction of A in both the streams is same. Enthalpy of both the streams is same. Okay, so over here uh, we have shown the condenser separately, and I hope you must have understood how what happens with the condenser, how energy flows into the condenser, how material flows into the condenser, and then how material and energy comes out of the condenser. Okay, so again I have shown the condenser separately. Now let us take total material balance. Again, let me tell you, we are discussing total material balance at steady state. What is the meaning of that? The meaning is we are neglecting accumulation. So it will be simply input of material is equal to output of material. Same is the case with energy balance. Input energy is equal to output energy. So let us first understand how to write total material balance. I have already discussed this while discussing material balance for tray column in one of my previous video. You please watch that video. So total material balance will be material is coming along with the stream into the condenser, and it is coming out along with the two streams. So it will be G1 is equal to L0 plus D. G1 is input, L0 and D they are output. So it will be G1 is equal to L0 plus D, and I am calling that as equation number 1. Okay. Now component material balance. Here we are going to consider the more volatile component. Component material balance will be discussed in terms of more volatile component. So it will be total flow in to the condenser into mole fraction of A in it. So G1 Y1 is equal to total reflux flow out of the condenser into mole fraction of A in it. So it is L0XD, and similarly plus D, total molar flow rate of distillate into mole fraction of A in it. So component material balance, that is material balance for component A, will be written as G1Y1 is equal to L0XD plus DXD, and I am calling that as equation number 2. Now let us write energy balance. Again we are going to write it at steady state. Input energy is equal to output energy. So if you look at the schematic over here, energy comes along with this stream, and it is leaving along with this stream, along with this stream. So energy comes with the material stream, it leaves with the material stream, plus you are removing heat from the condenser. The rate of heat removal is QC. So that has to be considered. So it will be heat coming with this stream, energy coming with this stream is equal to energy going out with this stream plus energy going out with this stream plus energy that is removed as heat from the vapors. So it will be G1 Hg1 is equal to L0 plus L0 Hd plus D into Hd plus Qc. Now let us understand how this you have this. For example, energy associated with G1, we are expressing it as G1 Hg1. Now G1 is molar flow rate, kilomole per second. So let me show you. So G1 is kilomole per second. Kilomole per second. Just a minute. Kilomole per second. Whereas this enthalpy, we are expressing it as energy per unit mole. So it will be kilojoule per kilomole. Okay. So you have multiplication of this two. So what happens? This kilomole and kilomole will be going getting cancelled, and you are left with kilojoule per second. you are left with kilojoule per second. That means each term will be having a unit of kilojoule per second. So rate of heat energy in is equal to rate of energy out. So that's why we are expressing energy in with this term, flow rate, molar flow rate of the state into enthalpy per unit mole for that state. So that's why you have this equation G1 Hg1 L0 into Hd plus D into Hd plus Qc. Okay, so let us call that as equation number 3. Equation number 3 gives energy balance for the condenser. Now let us move ahead. Now what I'm doing, I'm calling I'm calling Q1 as the heat removed at the top per mole of the distillate. Heat removed at the top per mole of the distillate, and heat that is coming totally removed from the system. So condenser is at the top. So what if you look at this schematic diagram, you can easily identify what is happening at the top. Heat is coming out at rate QC, and heat is also going out along with energy is going out along with the distillate stream. So total energy or total heat removed will be heat removed in the condenser plus heat energy that is going out with the distillate stream. Okay, so I'm expressing this total heat removed at the top per unit mole of the distillate. So Q1 is representing that quantity of heat removed, total heat removed at the top per mole of the distillate. So if you have to express it mathematically, you can express in this way. Q1 is equal to QC plus DHD. QC plus DHD represents total heat that is removed at the top, and we are considering it per mole of the distillate. So simply Q1 will be equal to QC plus DHD upon D. Okay. So if I rearrange it, I can write it like Q1 into D is equal to QC plus D into HD. So I have taken D on this side. Now what we will do, we will use this in equation number 3. If you look at equation number 3, you have these two terms DHD plus QC. So these two terms can be replaced with Q1 into D. So if you do that, you have sorry, we have G1 Hg1 is equal to L0 into HD plus Q1 into D. Now you can easily identify we have replaced these two terms with Q1 into D. Okay, now let us move ahead. So previously we had got this equation G1 Hg1 plus L0 HD plus Q1 into D. I hope you remember this. Now what was equation 1 that we wrote? It was G1 is equal to L0 plus D, the total material balance. So what we will do, we will use equation 1, which is G1 is equal to L0 plus D in the above equation. So that will give us L0 plus D. So G1 now is replaced with L0 plus D. So L0 plus D into Hg1 is equal to L0 HD plus Q1 into D. Okay, so next I'll just simplify the equation. So I'll multiply Hg1 to the bracket. So L0 Hg1 plus D Hg1 is equal to L0 HD plus Q1 into D. Next, I'm taking L0 terms on one side, terms containing L0 on one side, and terms containing D on the other side. So it will be L0 Hg1 minus L0 HD, that is equal to Q1 into D minus D into Hg1. And in the next step, I'll take L0 common out on the left hand side and D common from on the right hand side. So it will be L0 into Hg1 minus Hd, that is equal to Q1 minus Hg into D. And it will be okay. The same step I have written. Now the equation is arranged in this way. D is brought on this side, so it will be L0 point is equal to Q1 minus Hg1 divided by Hg1 minus Hd. But if you look at the left hand side of this equation, you have L0 by D, that is reflux flow divided by distillate flow. L0 by D, if you know, it is nothing but R, that is the external reflux ratio. So that's why you have R is equal to Q1 minus Hg1 upon Hg1 minus Hd. Okay. So the purpose of taking energy balance, the purpose of discussing energy balance for the condenser, what was the purpose? The purpose was to get an equation for the reflux ratio, external reflux ratio. Okay. So uh, in my earlier video, enthalpy concentration diagram, distillation part 17, I have discussed about enthalpy concentration diagram. So with the help of enthalpy concentration diagram, you can get external reflux ratio by using this equation, Q1 minus Hg1 divided by Hg1 minus Hd. Okay. So that equation is important. Okay. So of course R in this case is the external reflux ratio. Okay. So the purpose of discussing, I hope now my objective is clear to you. We have now got equation for the external reflux ratio. Now let us move ahead. Now let us consider the entire rectifying section. We just had considered only the condenser, so as to have equation for the external reflux ratio. Now let us consider the entire rectifying section. So I'm showing over here, and we are taking the envelope. You should identify the streams that are coming into the envelope and those that are going out of the envelope. So this is one stream, Gn plus 1, Yn plus 1, Hgn plus 1, that is coming from tray number n plus 1. So that is going into the envelope. This stream, liquid stream coming out of nth tray, it is going out of the envelope. Then heat is removed, QC is going out of the envelope, and then distillate is going out of the envelope. So how many material streams? There are 1, 2 and 3 material streams. Are you understanding it? So one goes into the envelope and 2 are coming out, and there is one energy stream, that is the rate at which heat is removed from the vapors in the condenser. Okay. Sorry. So now let us first write the total material balance. Again, we are considering steady state material balance. Input is equal to output. So it will be, this stream is coming in, so it will be Gn plus 1 is equal to Ln plus D. Ln is going out, D is going out, and Gn plus 1 is coming. So this is Gn plus 1 is equal to Ln plus D, and I am calling that as equation number 5. Then the component material balance. So it will be written as Gn plus 1 into Yn plus 1, that is equal to Ln into Xn plus D into Xd. I am calling this as equation number 6. Of each term is a product of total flow into mole fraction of A, mole fraction of more volatile component. Okay. Then the energy balance, again at steady state, energy associated with vapor stream, energy associated with vapor stream that goes in is equal to energy associated with this stream that comes out plus energy associated with distillate that comes out plus the rate at which heat is removed in the condenser, that is QC. So it will be Gn plus 1 Hgn plus 1, that is equal to ln H ln plus d into Hd plus Qc, and let us call this as equation number 7. But as discussed earlier, we had got this equation. Q1 is total heat removed at the top per mole of the distillate, and after simplification we had got this equation. dHd plus Qc is equal to Q1 into D. So therefore, if you use this, we will get this equation. Gn plus 1 into Hgn plus 1 is equal to ln HLN plus Q1 into D. So in equation number 7, the last two terms, D into HD plus QC, these are this is nothing but Q1 into D, and that's why you get equation number 8. Gn plus 1 Hgn plus 1 is equal to ln into HLN plus Q1 into D. Okay. Now what we are going to do, we are going to use equation 5 in equation 6, one thing. And the other thing that we will be doing, the other task that we will be doing is we are going to use equation number 5 in equation number 8. Okay, so let us do this on the next slide. Okay, now let us continue. So we are going to use equation number 5 in equation number 6 and also in equation number 8. So equation number 5 is Gn plus 1 is equal to Ln plus D. Equation number 6 is Gn plus 1 into Yn plus 1 is equal to Ln into Xn plus D into Xd. And equation number 8 is Gn plus 1 into Hgn plus 1, that is equal to Ln into HLN plus Q1 into D. Okay, so we have got this equation previously. Now first what we will do, we will rearrange equation number 5. How? Let us understand. So rearranging equation number 5, I'll rearrange it like D is equal to G1 plus minus G1 Gn plus 1 minus Ln, and now I'm calling it as equation number 9. So from equation number 5 we have got equation for D, and I'm calling it as equation number 9. Now we will use equation 9 in equation number 6. So this is the equation. So in place of D we will be using Gn plus 1 minus Ln. So that will be Gn plus 1 into Yn plus 1 is equal to Ln into Xn plus, now in place of D we are going to use Gn plus 1 minus Ln. So Gn plus 1 minus Ln into Xd. So if you rearrange, it will be Gn plus 1 into Yn plus 1, that is equal to Ln into Xn, Gn plus 1 into Xd minus Ln into Xd. So Xd is multiplied with the bracket. Further, we have Gn plus 1 Yn plus 1 minus Gn plus 1 Xd, that is equal to Ln Xn minus Ln into Xd. So what we have brought Gn terms containing Gn plus 1 on one side and terms containing Ln on the other side. Then in the next step we are going to take Gn plus common, so it will be Gn plus 1 into Yn plus 1 minus Xd, that is equal to Ln into Xn minus Xd. Again, if you rearrange, you'll get Yn plus 1 minus Xd divided by Xn minus Xd, that is equal to Ln upon Gn plus 1. And let us call this as equation number 10. Okay. Now let us use equation number 9 in equation 8. That means in place of D we are going to use equation number 9. So it will be Gn plus 1 into Hgn plus 1, that is equal to Ln into HLN plus Q1 into D. Now D is replaced with Gn plus 1 minus Ln. In the next step, Q1 will be multiplied with the bracket. So it will be Gn plus 1 Hgn plus 1, that is equal to Ln HLN plus Q1 into Gn plus 1 minus Q1 into Ln. Okay. Now let us continue. From the previous slide we got this equation Gn plus 1 into Hgn plus 1, that is equal to Ln HLN plus Q1 into G1 Gn plus 1 minus Q1 into Ln. Now what will be the next step? We will collect terms containing Gn plus 1 on one side and terms containing Ln on the other side. So it will be Gn plus 1 HGN plus 1 minus Q1 GN plus 1 is equal to ln HLN minus Q1 into ln. In the next step, on the left hand side we will take Gn plus 1 common, whereas on the right hand side we will take ln common. So it will be Gn plus 1 into Hgn plus 1 minus Q1, that is equal to ln into HLN minus Q1. And if you rearrange it, sorry, we will write the equation will be Hgn plus 1 minus Q1 divided by HLN minus Q1, that is equal to ln upon Gn plus 1. Let us call this as equation 11. Okay. So previously we got equation 10. What was that? Yn plus 1 minus xd divided by xn minus xd, that is equal to ln upon Gn plus 1. So now you can compare equation 10 and 11. Each of the equation has this term ln upon Gn plus 1. So if you do that type of comparison, it will be ln upon Gn plus 1, that is equal to Yn plus 1 minus xd divided by xn minus xd, that is equal to Hgn plus 1 minus Q1 divided by HLN minus Q1. Now let us call this as equation 12. And you can say something about equation 12. Equation 12 it will be a straight line on enthalpy concentration diagram. I have already discussed enthalpy concentration diagram in my previous video. You please watch that video. So on the enthalpy concentration diagram, equation number 12 is a straight line, and this particular straight line, it passes through some points. Which are these points? One is having coordinates of xd q1. That point we will represent it by delta d on the enthalpy concentration diagram. So at the end I'll tell you how these points are plotted. Then there is one more point. I'm denoting that point by gr, and it will be having coordinates of yn plus 1, hgn plus 1. And there is one more point which I am going to denote by lr, and it will be having coordinates of xn hln. Okay, so we are talking about equation 12, and we have understood that this is equation 12 is representing a straight line on enthalpy concentration diagram, and this straight line, it passes through these points: delta d with these coordinates, gr with these coordinates, and lr with these coordinates. Okay, so let us move ahead. So that ends our discussion on energy balance for rectifying section. Now let us talk about energy balance for the stripping section. So for that, again I have shown the tray column. Now we are going to concentrate on the stripping section. So I am drawing an envelope that covers the stripping section, so you can easily identify what streams are going to be associated with this envelope. So feed stream, after feed stream enters on the feed plate, and now it will be no longer called as feed, because the reflux stream that is coming from n plate will be getting added to it, so that the resulting stream goes into the stripping section. Okay, the residue comes out of the stripping section. The vapor phase that rises from mth plate, it comes out of the stripping section, plus you are adding heat at the rate of QR into the stripping section. So I have shown it separately. Okay, so I'm considering the rectifying section, stripping section in this way. Okay, so let us again, to have perfect understanding, let us understand it. The notations that I'm going to use, we have considered see mth plate, m plus 1 plate, and the last plate in the column. Okay, the liquid stream that is coming from mth plate will be identified by L bar m, the liquid flow rate, xm mole fraction of A, HLM enthalpy per unit mole for this liquid stream. Similarly, liquid coming out of m plus 1th plate will be identified as L bar m plus 1 xm plus 1 and HL m plus 1. Flow rate, molar flow rate, mole fraction of A and enthalpy per unit mole. Then the liquid that is coming from last plate, that is the n plate, will be having molar flow rate of L bar n, mole fraction of A in it is Xn, and enthalpy associated with it is HLN. Okay, same liquid stream is taken out and it is sent to the condenser L bar n, Xn, HLN. It is sent to the reboiler. From the reboiler, you are removing the residue. For residue, molar flow rate is W, mole fraction of A in it is XW, and enthalpy per unit mole of the residue is HW. Okay, then within the after the vapor phase is created, it enters the column. The vapor stream that is leaving nth tray, it will be having molar flow rate of G bar n, Yn, Hgn. Then the vapor stream that is coming out of m plus 1 will be having molar flow rate of Gm plus 1, mole fraction of A in it is Ym plus 1, and enthalpy per unit mole for that vapor stream is Hgm plus 1. Okay. Then one more you can see vapor stream that we will be using in our discussion, and that vapor stream is the stream that coming out of the reboiler and then entering at the bottom into the column. So that vapor stream, it will be considered to be coming out of a plate that is next to nth plate. And what is that plate? N plus 1. So molar flow rate will be G bar n plus 1 for that vapor stream. Mole fraction of A in it will be Yn plus 1, and sorry, the enthalpy associated with it will be Hgn plus 1. Okay, and of course this is the vapor phase is created as you are adding heat at the rate of QR, kilojoule per kilomole. Okay, now for our discussion we are going to consider this envelope. So one material stream goes into the envelope, the liquid stream that is coming from mth plate. One material stream goes out of the envelope, that is vapor from m plus 1 plate. Okay, then one material stream that is residue stream that is going out of the envelope. So energy is coming into the envelope with this stream, energy is going out of the envelope with this stream, energy is going out of the envelope with this stream, energy is added to the envelope at this rate. Okay, so with this understanding we are going to take the material balance. So once again I have shown the stripping section. Now let us write total material balance. Total material balance at steady state. Now you can easily write. So input is equal to output. So this is input stream, and there is one input stream and there are two output streams. So accordingly the balance will be written as total material balance will be written as L bar m is equal to W plus G bar m plus 1, and I am calling this as equation number 30. Okay, and now component material balance, that is material balance for more volatile component. So how will this be written? This will be written as L bar m into xm total into fraction is equal to W into xw plus G bar m plus 1 into Ym plus 1. Let us call it as equation number 14. Now energy balance again at steady state. So it will be written as HLm into L bar m plus QR, that is equal to W into HW plus hgm plus 1 into g bar m plus 1. I have already told why the energy going in is represented by this product. I have just discussed. So this is energy per unit mole into molar flow rate. So the product gives us energy per unit time. Okay. So now let us move ahead. Now I'm defining one more parameter. Earlier, if you remember, we had defined Q1. Now I'm defining Q2. What is this Q2? Q2 is the net heat that is removed at the bottom per mole of the bottom product. So if you look at the bottom of the column, energy is going out with the residue and it is added to the reboiler at the rate QR. So the net heat that is going out will be heat going out with the residue stream minus heat that is added into the reboiler per mole. So accordingly, Q2 will be WHW. WHW represents heat that is going out with the residue stream minus QR, that is heat added to the reboiler. So net output will be WHW minus QR, and we are considering this net output per mole of the bottom product. So that's why equation for Q2 will be WHW minus QR upon W. If you rearrange it, it will be Q2 into W, that is equal to W into HW minus QR. Okay, so now let us continue. We will rearrange equation 15. Before that, what is equation 15? Let me tell you. Equation 15 is HLM into L bar M plus QR, that is equal to W into HW plus HGM plus 1 into G bar M plus 1. So how is the rearrangement? So this is like HLM into L bar M, that is equal to WHW minus QR into HGM plus 1 into G bar M plus 1. So what I have done, I have taken QR on the other side, but we just saw Q2 into W is nothing but W into HW minus QR. That means this can be replaced with Q2 into W. So the same thing we will be doing. So we have HLM into L bar M, that is equal to Q2 into W plus HGM plus 1 into GM plus 1, and I'm G bar M plus 1. I'm calling this as equation number 16. Okay. So now we have let me tell you. So rearranging equation 12. What was equation 12? Equation 12 was L bar M is equal to W plus GM plus 1, G bar M plus 1. Okay. Now it is arranged as W is equal to L bar M minus G bar M plus 1, and I'm calling that as equation 17. Now using equation 17 in equation 14. So we are going to use equation 17 in equation 14. What is equation 14? Equation 14 is L bar M into XM, that is equal to W into XW plus G bar M plus 1 into YM plus 1. This is equation 14. Now we are going to use equation 17 in equation 14. So it will be L bar M into XM, that is equal to, in place of W we are going to use L bar M minus G bar M plus 1 into XW plus G bar M plus 1 into YM plus 1. Now let us simplify. So it will be L bar M into XM, that is equal to L bar into XW minus G bar M plus 1 into XW plus G bar M plus 1 into YM plus 1. Then all terms containing L bar M on one side. So it will be L bar M XM minus L bar M XW, that is equal to minus G bar m plus 1 xw plus g bar m plus 1 ym plus 1. Okay, so now on the left hand side we will take L bar m common, so L bar m into xm minus xw. On the other side we will take g bar m plus 1 common, so it will be g bar m plus 1 into ym plus 1 minus xw. And now we will arrange the equation like L bar m divided by g bar m plus 1 is ym plus 1 minus xw minus xm minus xw, and I am calling this as equation number 18. Okay, so this is one thing. Now the next task is we will be using equation 17 in equation 16. Sorry. So in place of w in equation 16 we will be using this equation. So it will be h lm into L bar m, that is equal to q2 into L bar m minus g bar m plus 1 plus hgm plus 1 into g bar m plus 1. Okay, so in this way we will be using we'll be getting this equation. Okay, so let us continue. So we have got this equation HLM into L bar m, that is equal to let me say it once again, HLM into L bar m, that is equal to Q2 into L bar m minus G bar m plus 1 plus HGM plus 1 into G bar m plus 1. Okay, in the next step we will be multiplying Q2 with this bracket, so accordingly we will get HLM into L bar m, that is equal to L bar m into Q2 minus G bar m plus 1 into Q2 plus HGM plus 1 into G bar m plus 1. So all L bar m term on one side, so that will give us HLM into L bar m minus L bar m into Q2, that is equal to minus G bar m plus 1 into Q2 plus HGM plus 1 into G bar m plus 1. Okay, and the next step, L bar m common on the left hand side and G bar m plus 1 common on the right hand side. So it will be HLM minus Q2 into L bar m, that is equal to HGM plus 1 minus Q2 into G bar m plus 1. Now you can rearrange this equation as L bar m upon G bar m plus 1, that is equal to HGM plus 1 minus Q2 divided by HLM minus Q2, and let me call this as equation number 19. Okay, so G bar m plus 1 is brought on this side and then we get this equation. The next task is we will compare this with equation 18 which we had got earlier. So that equation 18 is L bar m divided by G bar m plus 1, that is equal to ym plus 1 minus xw divided by xm minus xw, and now you have equation 19. So both equation 18 and 19 they have L bar m upon G bar m plus 1 in them. So that's why sorry, we can arrange the equation like L bar m upon G bar m plus 1, that is equal to HGM plus 1 minus Q2 divided by HLM minus Q2, that is equal to ym plus 1 minus xw divided by xm minus xw, and I am calling this as equation 20. What can you say about equation 20? Equation 20 is a straight line on the enthalpy concentration diagram, and this line it passes through the following points. Which are this point? One is having coordinates of xw q2. We are going to represent that point as delta w. The other point has coordinates of ym plus 1 hgm plus 1. We are going to represent that as gs on the enthalpy concentration diagram. And the third point is xm hlm. We are going to represent that as ls on the enthalpy concentration diagram. ठीक है. So equation 20, which is a straight line on the enthalpy concentration diagram, it passes through these points. ठीक है. Okay. Now we will discuss energy balance for the entire column. So we will be using this envelope. So feed goes into the envelope, distillate comes out of the envelope, residue comes out of the envelope, heat comes out of the envelope at a rate of QC, heat is added to the envelope at a rate of QR. ठीक है. Total material balance will be feed is equal to distillate plus residue. Sorry, that is we are going to take steady state material balance. So F is equal to D plus W. Let us call it as equation 21. Then component material balance total into fraction, that is F into XF, that is equal to D into XT plus W into XW. Let us call this as equation 22. Energy balance is energy with the feed stream, F into HF, that is equal to energy with the distillate stream, THD, plus energy with the residue stream, that is WHW. I'm calling it as equation 23. So first thing, we will be using equation 21 in 22. So it means in place of F we are going to use D plus W. So it will be D plus W into XF, that is equal to D into XD plus W into XW. ठीक है. So now we are doing this. We are using equation 21 in equation 22. So we get this D plus W into XF, that is equal to D into XD plus W into XW. If you simplify it, we will be getting D into XF plus W into XF, that is equal to D into XD plus W into XW. All D terms on one side. We have D into XF minus D into XD, that is equal to W into XW minus W into XF. D common on the left hand side and W common on the right hand side. So that is D into XF minus XD is equal to W into XW minus XF. That is D upon W is XW minus XF divided by XF minus XD. I'm calling it as equation 24. Now the other task that we will be doing is we are going to use equation 21 in equation 23. Equation 21 is F is equal to D plus W. Now we have to use it in equation 23. Equation 23 is HF, that is equal to DHD plus WHW. Now in place of F we are going to use D plus W. So therefore we have D plus W into HF, that is equal to D into HD plus W into HW. We'll simplify further. D into HF is equal to W into HF plus that is equal to D into HD plus W into HW. So that is D into HF, all D terms on one side. So D into HF minus D into HD, that is equal to W into HW minus W into HF. D common, W common on the other side. So D into HF minus HD, that is equal to W into HW minus HF. And if you rearrange it, you'll be getting D by W is equal to HW minus HF divided by HF minus HD, and I'm calling it as equation 25. So now we are going to compare equation 25 with equation 24, which has one term common, that is D upon W. So from equation 24 and 25, we can write D by W is equal to XW minus XF upon XF minus XD, that is equal to HW minus HF upon HF minus HD, and I'm calling it as equation 26. Okay, so we got equation 26. D by W is equal to XW minus XF divided by XF minus XD, that is equal to HW minus HF divided by HF minus HD. So equation 26 is a straight line on the enthalpy concentration diagram, and it passes through 3 points. Which are these 3 points? Let me tell you. So it passes through delta D, which was understood earlier. it has coordinates of xd q1, then F, which has coordinates of xf hf, and delta W, which was again understood earlier, it has coordinates of xw and q2. Okay. Now in this way we complete our discussion on energy balance, and we had got three lines, and now how those three lines are to be represented on the enthalpy concentration diagram. How to do that, let me tell you. First I'll show you the enthalpy concentration diagram. So you have enthalpies plotted on y-axis, enthalpies of the liquid stream and enthalpies of the vapor stream, HL and Hg respectively, on y-axis. On x-axis, we are going to plot the mole fractions. X, mole fraction of A in the liquid stream, Y, mole fraction of A in the vapor stream. So this n represents x is equal to 0. This n represents x is equal to 1. You have this the result of plot of x versus, that is mole fraction of A in liquid versus enthalpy of liquid. This gives the lower curve, whereas a plot of mole fraction of A in vapor phase versus enthalpies of vapor phase gives the upper curve. Okay, so at x is equal to 0, the vertical distance between the two curves, it will give enthalpy of pure B. X is equal to 0, that means no A, so you have just B in it. At x is equal to 1, that means you have only A, so that A represents pure A. So the vertical distance between the two curves will give latent heat of vaporization of E. Okay, and we have these points which we got in our discussion. One was delta D with coordinates of xd q1, then gr with coordinates of yn plus 1 hgn plus 1, lr with coordinates of xn ln hln. So this delta D will be represented over here. So this point will be having coordinates of xd q1. Delta D will be represented in this way on the enthalpy concentration diagram. Then gr will be lying on the upper curve, somewhere on the upper curve, and lr, a line will be passing, a line passing through delta D and gr will meet the lower curve, and that lower curve will be nothing but this point LR. Okay, so on enthalpy concentration diagram, the 3 points delta D, GR and LR, they are represented in this way. Okay, we also got the other 3 points. One was delta W with coordinates XW Q2, GS with coordinates YM plus 1, HGM plus 1, and LS with coordinates XM LM, HLM. Okay, so point delta W will be represented over here. Point LS will be lying on the lower curve. And if you draw a straight line through delta W and LS, it will meet the upper curve at the point GS, which is having coordinates YM plus 1, GM plus 1. Okay, so in this way, these 3 points are represented on the enthalpy concentration diagram. Then energy balance for the total entire column gave us these 3 points. F with coordinates XF, HF. So in order to get those points, what we will do, we will delta D and delta W, again they are lying on the straight line, and point F will be lying on this line, the line that connects delta W, delta D. So depending on the condition of the feed, point F will be located, but it will always be located on the line delta W, delta D. You have to note that. Okay, so for example, over here, F is representing pure liquid. Not sorry, the feed is a liquid solution. So if point F was lying on the lower curve, in that case, feed would be saturated solution, saturated liquid solution. We are going to talk about it in our next videos. In future videos, I'll be discussing in details over that. Okay, so for time being, you can now easily understand energy balance for the tray column gave us these 3 points, and now we know how these 3 points, or not 3 points, all these points, they are represented, or they can be represented on the enthalpy concentration diagram. So with this, I end my discussion for this particular video. I have discussed the total energy balance for the entire column. I hope you have understood the concepts. If you have any doubts, you please mention your doubts in the comment section. Thanks for watching my video. Please do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you'll be notified as soon as I upload any new video. Please be with me. If you really like my videos, hit the like button as well. Thank you for being with me for today. We will meet in our next video. Thank you.